Hi again, Dr. Bettina Heinz here to continue with atomic theory. We had an intensive section where we dealt with spectra, with video material as well. So we have to continue with section 4 because we didn't cover all the bases. So today we will go into more of the quantum mechanical model of the electron shell, or of the atom to be exact. So we will start with our topics. We talked a lot about the spectra, of course, the Bohr model. Remember, we also introduced in section 3, part 3 of our atomic theory material. And Bohr, remember, he looked at the atomic model sort of like a miniature planetary system where the electrons orbit around allowed energy level zones encircling the nucleus. He considered the electron still to be a particle which can be followed around quite nicely, but in reality, remember, the electron is not such a controllable body. It has very high speeds. So we know it's going to be in these orbits, but we don't know exactly when and where at a certain point it would be found. Heisenberg stated this uncertainty relationship. That means at the same moment you cannot determine the electron's position or location and its momentum. So that means we have to look at the electron as a very evasive body. I always like to compare it to a Mickey Mouse in a cartoon that runs real fast. You would give it a swish effect or a smear of the action. That means it's so fast. Or what is really good to consider as an example is the picket fence. And you drive by really fast, you wouldn't stick your arm out because the picket fence is hardly visible anymore. It's like a big smear of light, or an image rather. So the same thing is the situation with the electron. So what we can only do is look at the probability area of the electron. And this can be determined by the Schrödinger function when you use different energy levels, and then you can determine what kind of space, probability space, is found for the electron at different energy levels. So in the ground state, in the lowest energy level, you can find the electron somewhere around the nucleus in a type of spherical geometry. So in a spherical type of space, we can find the electron there somewhere. Just like we people have a certain probability area, we will be at work or at home or maybe shopping. So we can sort of figure out where an individual is to be found. Detectives certainly know about all this. So the same way we can find out the probability area of the electron, but we cannot zero in on it because of the Heisenberg's uncertainty relationship. So this is the distribution pattern, the average distance from the nucleus. So you have the probability somewhere close to the nucleus, but also very far away. But mostly we have a certain abundancy at a given distance from the nucleus. So we can say it's sort of like a shell shape when the electron is in its ground state. Now when you raise the energy level, the probability area seems to change all of a sudden. It becomes a so-called P-shaped orbital, or number 8-shaped orbital. We call this, however, the P orbital. And once it has these two lobes, it's almost as if you take a sphere and cut it in half, and you get two lobes or two nodes, and you have the node in the middle with the two lobes, and then you can shift it in the presence of a magnetic field to different positions around the coordinate axes. And we have an example here that I'd like to show you. This is a model of a so-called s orbital, which means we have the spherical distribution area. So the electron is somewhere in here to be found. So if I point here, it might be there, it might be here, it might be there, it might be there, but it can be further away, but it can also be closer to the nucleus. But these are the most abundant or most common areas where the electron can be found. So you see it's spherical. We have here the y-axis, the x-axis, and the z-axis. So this would be an s orbital. Next we have what we just showed with the probability area in the shape of a number 8. And you see here, or bell-shaped you can sometimes say. And we have here also the possibilities. Because we have an axis here, it can be aligned in different areas of space. And this is what is done by outside magnetic fields or under the influence of magnetic fields. You can shift the position or the alignment of this so-called p orbital in 3 different ways. For instance, this might be the px orbital, or rather pz in this case. Then we have the py orbital on the y-axis and the px orbital on the x-axis. So it can be this way, or this way. So 3 possible alignments are observed. When you continue to raise the energy levels, you have another type of probability space, which is called a D-type space. And under the influence of a magnetic field, you can have 5 possible alignments after you calculate the psi function, the wave function. You get 5 possible alignments around the coordinate system. And notice that there's another cut of the orbital, like the p orbital cut in half would give you 4 lobes. And that's sort of the clover leaf-shaped orbital. These are called the d orbitals. And they can also be aligned differently in space. And so they have different coordinate dimensions. There's one funny one that is sort of number 8 with a donut around it. This is also a d orbital. It just turns out that the wave calculation produces this type of probability space. So as we go further out from the nucleus, we get more and more variations in probability areas, which is all a result of the wave function. So the electron follows practically the confines of the wave function that Schrödinger developed. Here we have another overview of these orbitals. As I already mentioned, these are probability areas in space. And in the end, we can sort of define certain quantum numbers for the electron as we go through the ladder of the different energy levels. I've failed to mention that we also have the f orbitals, which are 7 possible different types. And this, you see, it's almost like cutting a d orbital in half again. All the lobes, cut them. And then you get 8 lobes instead of 4. You see, this would be an example of an f orbital. So we have 7 different types. And there is one similar to this one, only that it has 2 donuts around it. And as you can go on and on mathematically, this can be done forever. But nature has its limits. Remember, we have only 7 shells. So the actual reality of these orbitals is limited to the f orbitals. But conceptually, we could have G and H orbitals and on and on. So we have quantum numbers that determine in which main shell the electron is. So that's called the n quantum number, or the main shell. Then we have the so-called azimuthal quantum number, which is L. That means when we have the possibility of alignment in space, then L would determine that. So we have the multiplicity of these orbitals in different orientations in space. So the L would be 3 possible alignments, which we have seen with the p orbitals. And then we have the magnetic quantum number, and which is symbolized by m, or nowadays with m subscript L. So that is the shape of the orbital in different magnetic orientations. So the shape of the orbital is p, for instance, in this example. But if it's on the x or y or z axis, that would be the azimuthal characteristic of that orbital. And last not least, we have the quantum number, the 4th quantum number, which is called the ms quantum number, or the spin quantum number. This relates to the electron really as a particle, because as a particle you have a rotational axis. If you consider the electron to be a tiny little sphere, it would have a rotational axis around, rotational movement around its axis, so it can be either right-handed or left-handed, and this is called the spin of the electron as a particle. So this would be the 4th quantum number, the ms, or sometimes also just considered s. So here we see in the picture the orientation around its own axis. And a symbol of determining orbitals is either a circle or a box, and this would be an atomic orbital. It represents an atomic orbital, and an atomic orbital is any probability space. And in each of these spaces, only 2 electrons can be housed. But they cannot have the same spin number. They have the same n, the same L, the same ml, but they have to have different spins. That means they have to differ in ms. And this is what we call the Pauli principle. Pauli, a German scientist, said that no 2 electrons within an atom, in the ground state of course, cannot have the same set of 4 quantum numbers. They have to differ in at least 1. So if they have all 3 the same, like n, m, l, ml, they have to differ in the spin. So each orbital, each probability space has room for 2 electrons, but they have to be in opposite spins. And this is how we characterize that, with a little box or a circle, and an arrow pointing up is an electron with 1 orientation of spin, and an electron pointing down is the electron with a counter spin, or the opposite spin orientation. And then that orbital is complete. And we see here also in the diagram the different magnetic orientations in space according to the 3 axes. Here we have sort of the orbital tree, as you might call it. And the orbital tree tells you how many of each type of orbital we have. The multiplicity. It's almost like a nice little tree. We have here the s orbital, and we also have the symbol or the formulation of an s orbital in the form of a little box. And we have the orientation. There's only 1 type of s orbital. Therefore, the azimuthal quantum number is 0. When we have the p orbitals that we can only find in the 2nd shell, then we have 3 possible orientations, the px, the py, and the pz. And here we have the 3 boxes that symbolize each of these orbitals, which can each house 2 electrons with opposite spin. So that means all of these 3 p orbitals can house together 6 electrons. 2 in each. Now these orbitals are called degenerate. What does that mean? That means they have no distinction between them, energetically speaking. They're on the same energy level. They might have a different orientation, but they're equal in energy, and we call that degenerate. And this is very interesting for later when we fill in orbitals systematically. Then degenerate orbitals have to be filled separately by one electron before they can be doubled up to the proper number. This is called the Cont'd rule of maximum multiplicity, or degenerate orbitals are filled separately before they are doubled. Now we see here the different orientations of the d orbitals. There are 5 possible ones. Some are right on 2 axes, some are sort of in between the axes. And here's our funny one with a donut that we have already shown in our model. And here we have L equals 5. We have 0, -1, -2, and +1 and +2. So the multiplicity is 5. And here we have the G, excuse me, don't want to jump ahead. These are the F orbitals. And we always have 8 lobes. And they're very difficult to remember in their spatial arrangement. But we have also these funny ones with the 2 donuts. In a way, we're starting again with a P in a sense. Think about it. So that is our orbital tree. Remember, the atoms don't look like that. No, I'm sorry, the electrons don't look like that, but they're found in these probability spaces. So if you want to find an electron, you have to look around in these spaces. It will be somewhere, because that's where its major probability of existence or presence is at a certain time. So there's a lot of variation for the little electron around hydrogen to move about in, depending on the external energy conditions. Now, if we look at the other atoms with many more electrons, you can understand that it's quite a complex structure. Now, when we look at an atom, like for instance carbon, then we can determine its electron configuration. What does that mean, the configuration? That means in what orbitals are the electrons to be found. Now, carbon is not as simple as hydrogen. It has 6 electrons. And we can tell by its nuclide representation, the atomic number is 6. 6 protons means 6 electrons. So we have to put these electrons into the proper boxes, you can say, into the proper places. Now, when we build up the electron shell, the main shell of n equals 1, the quantum number 1, will have an s orbital available. And this s orbital, as you remember, can house 2 electrons, but they have to be opposite spins. So that means you can indicate this by the designation 1s to the 2nd power, meaning it is complete with 2 electrons. And each of them have opposite spins, of course. But once this is full, no other electrons have room anymore in there. They have to go to a higher story of the electron shell hotel, you can say, and they go to the 2nd shell, and each shell begins again with the set of orbital types. So these are what we call sub-energy levels. Therefore, they're in the main energy level, split into different variations of sub-energy levels. So you start over again with S. The S sphere now is a little bigger than the inner one, and it can also house 2 electrons to become complete. Now, there's no degeneracy in the s orbital. There is only one type. So the Hund's rule doesn't have to be worried about. However, when the 2nd shell is filled with the s orbital, or the s orbital of the 2nd shell is already complete, then the next electrons have to move somewhere else. And remember what Bohr established, that the 2n square rule applies. That means the 2nd shell can house a maximum of 8 electrons. 2n square, n equals 2, 2 squared is 4 times 2 is 8. So the S is done. So what do? We move a little higher to a higher energy level, and we come to the p orbitals that are part of the second shell. Energy-wise, they are higher, but in space, they are encapsulated sort of by the s orbital, like a wrapping effect of the p orbitals will be observed. So the p orbitals are now starting to fill up with the electrons. But remember, carbon already has 4 in the s, so we only need 2 to fill up the p orbitals. There's still enough room for others, but remember, carbon is limited to 6 electrons. So this is how we would write the electron configuration. The exponents tell us how many electrons are involved in these spaces. An orbital diagram, on the other hand, will not stop with these plain letters and numbers. Here we'll put in the boxes or circles. You have a choice of either one. And then we fill in the electrons as follows. Like 1s, remember, has 2 electrons with opposite spin. It's complete. Then we have the 2s with 2 electrons. It's also complete. And then we have room to move around in the p orbitals. The 2 remaining electrons will then, according to Hund's rule, careful, will fill up the orbitals separately. So they're not doubled up right away, but they're filled separately with with parallel spins. Here we have anti-parallel, but when we fill up degenerate orbitals, they will be parallel first, and then later the opposite spins will come in. And this is the energy diagram of these orbitals. Here we have the lowest energy level is the 1s. The next energy level is the 2s. It's higher because we're in a higher shell. But part of the second shell are also the p orbitals, the 2 p orbitals. And we have shown that carbon has this type of energy distribution of its electrons. And you see, Pauli's principle also applies. No 2 electrons have exactly the same 4 quantum numbers. Look at these. They have a different azimuthal quantum number. Even though they have the same spin, they're in different orbitals, so they are different in at least the 3rd quantum number. So you will get more and more familiar with this way of depicting different elements or different atoms according to the electrons. Now, carbon is a simple element. Could you imagine of doing uranium with its 92 electrons and fill them in? It can be done because uranium is the last natural element in the periodic table of the elements, and it will fill up already some f orbitals, as you can guess. Here we have some images of our important scientists. Wolfgang Pauli, an Austrian, developed the Pauli exclusion principle. That means, again, that no 2 electrons can have the same set of 4 quantum numbers. Werner Heisenberg, who phrased or set up the uncertainty principle, which means that the electron is very difficult to pinpoint location and momentum, which is mass times velocity, cannot be determined simultaneously. And Friedrich Hund, who I have seen personally, I have heard his lecture in Germany personally, and he was already pretty old, but still a young, spry type of person in mind. He developed the rule for maximum multiplicity, which of course can be extended to the filling up of the orbitals if they are degenerate, first with parallel spins and then with anti-parallel spins. That means first singly, then doubly. And I have noticed that many scientists reached a ripe old age. Hund certainly did. Pauli and Heisenberg not quite so high. But Heisenberg wrote an interesting book about his memoirs. He talked a lot with Niels Bohr in Denmark, and Pauli and Hund, they all knew each other, and Einstein also. So that's very interesting reading. Here we have the quantum numbers again, and the different rules which are so important for this field. So an overview. And it's really not that difficult, it's pretty systematic, even though a lot of work went into this material. N is the main shell number, or the main quantum number. So it can be the first, second, third, fourth main shell, which is K, L, M, N, O, P, etc. Small l is the azimuthal quantum number, which determines the shape of the orbital. It goes from 0 to n minus 1. So if we have the second shell, L is only 1. If we have the third shell, L is 2, etc. So here we have the s orbital, the p orbital, a d orbital, and an f orbital. And then we have the magnetic orientation of the given orbitals, the possible magnetic orientations, which is the magnetic quantum number, or ML for short, because L is the shape which can be directed in different directions. So we have here, for instance, the example Py, Px, and Pz. So that is a result of magnetic influence. And then last not least, remember we have the spin quantum number, which is often characterized as Ms. And the spins, by the way, are given by numbers plus 1/2 and negative 1/2. Plus 1/2 means maybe right-handed, and negative means left-handed. Or illustrated by an arrow. The arrow up would indicate one spin. The arrow down would indicate the other spin, or the opposite spin. And you see here very nicely how the little electron is orbiting around its axis in one direction, and here in the opposite direction. So, Pauli principle, again. No two electrons have the same set of the 4 quantum numbers. That's pretty straightforward. Then we have Heisenberg principle, location, and impulse. He said impulse. In Germany you say Impuls, but it means actually momentum, or the degree of movement. Here we see momentum in our English terminology. Cannot be determined at the same time. So this is what we call the uncertainty of the electron. And Hund's rule means that degenerate or equal energy orbitals, meaning all p's, all d's, all f's, will be filled up separately with electrons after they are doubled. And with this, we will conclude this part of our atomic theory program. Thank you very much.